Swayam Prabha. Digital India. Educated India.
Welcome back. Let's take a look at faster multipliers, namely an order log n square multiplier. So this is fairly simple to construct. So let's consider an n-bit multiplier and an n-bit multiplicand. So if we write the multiplier and the multiplicand, multiplier here and the multiplicand here. So what we can do is we can construct n small n partial sums. Constructing each partial sum is very simple, and also it can be done in parallel. So whenever we have a 1, we write the multiplicand as is. If we have 0, we just write zeros. And every partial sum is offset by one position to the left as compared to the partial sum before it. So if we are multiplying n bits, we'll have n partial sums, small n, mind you. So all of these partial sums can be generated in parallel. So this partial sum can be generated simultaneously with this, which can be generated simultaneously with this. So generating all the partial sums is very easy. It takes a constant amount of time. So after that, we need to add n numbers. All right. So for adding n numbers, what we can do is we can have a tree of adders. So we can add the first and second here. We can add the third and fourth numbers here. The n minus 2th and n minus 3th numbers here. And so similarly, we can have a tree of adders. So if we take a look at the sizes of the numbers, the first partial sum is n bits long, and the last partial sum is 2n minus 1 bits long, right? So this is n over here and n minus 1 over here, n minus 1 zeros. So at each level, adding even 2n, even numbers with 2n bits would take order of log 2n time, which is the same as order of log n time because we ignore constants, and even the base of the log is not important. So after that, we have log n levels, right? Because in each level, we reduce the number of numbers that we need to add by a factor of 2. So now if we realize that we have log n levels and each level takes maximum of log of 2n time because there are 2n bit numbers, which is the same as log n because we always ignore constants in our work. So the total time taken is the number of levels, right? The number of levels multiplied with the time per level, which is log n times log n, which is order of log n square. So this is the complexity with our new multiplier that we have, and this is significantly better than our previous complexity, which was order of n log n, right? So log n square is much better than n log n, so this is a far faster multiplier in that sense, but we can do better. We can do much better as it turns out. So before we discuss how we can do better, it is important for me to mention that there is a new kind of device that we should use, we can use, and we have to use. It's a carry save adder. So what the carry save adder does is that it takes three numbers A, B, and C, and it generates two numbers D and E such that A plus B plus C is equal to D plus E. So essentially it takes three inputs, which are the three numbers, and it produces two numbers as output, such that the sum of D and E in this case is the same as the sum of A plus B plus C. So the way that we can do it is like this. So let's consider a 1-bit carry save adder or a CSA adder. So let us add 3 bits A, B, and C such that A plus B plus C is equal to 2D plus E. So D and E are also single bits, and this can be done. So I'll tell you why this can be done. So let us consider, the smallest values of A, B, and C and the largest values. So the smallest values are 0, 0, and 0. So we'll have D as 0, where the sum is 0, and we'll have E as 0. If we consider the largest values, which are 1, 1, and 1, then the sum is 1 plus 1 plus 1, 3, which is 1, 1, which is pretty much equal to 2 times 1 plus 1. So in this case, D is 1 and E is 1. So what we can do is that if we add A plus B plus C, right? So since we are adding three 1-bit numbers, the potential output, right, can be a 2-bit number as we just saw in this case. If we, let's say, we can, conveniently set, so in the 2-bit number, the left bit is the carry bit and the right bit is the sum bit. So you set this bit to D and this bit to E, then the value of this number would be equal to 2D plus E, which is exactly what we need. So what we see is that in the case of a 1-bit CSA adder, D and E can be computed as follows: that D can be the carry bit, right, the more significant bit, and E can be the sum bit, which is the less significant bit, the lesser significant bit in that sense. So let me just explain once again. If you're adding three 1-bit numbers A, B, and C, the smallest value is 0 and the largest value is 1 plus 1 plus 1, which is 3, which is 1, 1. So the final result will fit in 2 bits. So if I keep the 2 bits over here, let me do one thing. So let me call the sum bit, which is this bit, as E, and let me call the carry bit, which is the more significant bit, as D. So as we can see, the final result can also be expressed as 2D plus E, which is exactly what we want to do, right? So this is exactly what we want to do. So we basically have A plus B plus C is equal to 2D plus E. So if I take a look at the previous diagram, what I have done is I have taken three 1-bit numbers and produced two numbers, where 2D can be thought as capital D and small e can be thought as capital E. So I basically produced two numbers, so the sum of these two is equal to the sum of these three. Now let's do this for more bits, right? At the moment, A, B, and C were only 1 bits each. So let's consider wider versions of A, B, and C. So let us do a little bit of algebra to compute two numbers D and E, such that A plus B plus C is equal to D plus E. So the way that we will do it is that we'll use the same logic that was used here, and we'll just extend our results. So let us express A as a sum of its bits. So any number A can be expressed as, so let me consider A, right? And let the bits in A be A1 to AN. So let the number A be AN to A1. So this can be expressed as this number here is A. Similarly, we can express B in the same way as a sum of powers of 2, and each power is multiplied with the corresponding bit of B. And we can do the similar thing for C. Then what we can do is we can group all the terms together as AI plus BI plus CI and multiply them with 2 raised to the power I minus 1. So what we have seen in the previous result for 1 bit This can be expressed as 2 times 2 di plus ei times 2 to the power I minus 1. This is something that exactly we have seen here. So we can do the same. The same thing, sum of 3 bits is the same as sum of 2 numbers. Once we do the same, we can so this, since we have seen in the previous slide number 76, I'm not repeating. Once we have done this, again we can break up this expression over here. So we'll have two terms, I equal to 1 to n di times 2 to the power I. So this is one binary number, right, which we can treat as d. And this is one more number, which we can treat as e, right? So what we see here is that we have replaced the sum of a and b and c, a plus b plus c, as two numbers d and e. Right? So let me just get rid of the ink and you'll be able to see it better. Computing d and e is also very easy. The reason computing it is very easy is that we take, so in parallel, we consider, so since it's hardware, everything is parallel, so we consider the corresponding ith bits. We add them, so we get this d and e, where e is the sum bit, as we have seen just before in the previous slide. Oops, sorry. Yeah, e is the sum bit and d is the carry bit, right? So as we have seen here, we just add them up. Then all that we need to do is that so actually what we can do is that here we can take the 2 out and this will become di times 2 I minus 1. So this is one binary number which is composed entirely out of the sum bits where after adding individual bits, and this is one more binary number which is composed entirely out of the carry bits, right? Carry that is obtained by adding the 3 bits at the same positions. So once we get E is as is, but once we get this number, we just left shift, we multiply it by 2, which means left shifted by one position, and we get the number D. So essentially computing both D and E can be done very quickly in constant time or in order 1 time. And the way it is done is that we consider the ith bit of all three numbers A, B, and C. We add three 1-bit numbers. This can be done in parallel, so we'll get a sum bit and a carry bit. So we form one number just with the sum bits of all the individual sums, right? And one more number with the carry bits that we obtain by adding all triplets of numbers, right? Of the form AI, BI, and CI. And then we just take the number that we get and left shift it by one position, which is to effect this multiplication by 2. And one number becomes D and the other number becomes E. So this can be done, so this particular step of extracting the ith bit, adding the three ith bits, getting DI and EI, all of this can be done in parallel. So this takes constant time. Then forming the number with these bits also takes constant time. And left shifting also takes constant time. So it's not an issue, right, by one position. So that's the reason getting D plus E from A plus B plus C, the entire operation is a constant time operation. So it's just a summary of what we just discussed. How do we generate D and E? Well, we add all the corresponding sets of bits AI, BI, and CI independently, right? Simultaneously, independently, and simultaneously. We set DI to the carry bit produced by adding AI, BI, and CI, and we set EI to the sum bit produced by adding AI, BI, and CI. So since all the operations are done in parallel, it takes order of 1 time. So let's now discuss the Wallace tree multiplier. The idea is like this, that we generate n partial sums. So this, as we have seen in the previous example, can be done very quickly. So this can be done in order of 1 time, where we generate the n partial sums. How do we do this? We take a look at each bit in the multiplier. If it is 1, the partial sum is the multiplicand, of course shifted by a certain number of positions to the left. Otherwise, the partial sum is 0. So this is exactly what we do. If the ith bit in the multiplier is 0, the partial sum is 0, pi is 0. Otherwise, the pi is the multiplicand left shifted by I minus 1 positions. if the ith bit in the multiplier is 1. So this can be done in parallel. Once we have n partial sums, we can use a tree-based adder uh, to affect the multiplication. The way this is done is like this, that we have a similar tree as we had in the log n square multiplier. So in this case, what we do is that we divide our n partial sums into groups of 3. We have a carry save adder, a CSA adder that takes in 3 inputs and that produces 2 outputs. So this adder produces 2 outputs, and then the next adder, one output is sent here and one more adder is sent to another carry save adder, which takes 2 outputs from here and the 2 outputs from the next partial sum adder, right? From the next CSA carry save adder. So in this case, if we have, so basically each carry save adder here is decreasing the number of inputs by 3 by 2, right? So if there are 3x inputs here, there are 2x inputs in the next level. So what we do is that we create a tree of adders where we start with the partial sums and keep on adding them. So recall that the carry save adder takes 3 inputs and produces 2 outputs, where the sum of the outputs is the same as the sum of the inputs. Then what we do is that we keep on adding levels till we finally have a case where we have only 2 outputs, and the sum of these two is the sum of all the partial sums. So the approximate number of levels that we will require is order of log of n to the base 3 by 2. Why 3 by 2? It is 3 by 2 because at every level we are decreasing the number of partial sums by a factor of 3 by 2. So we are just adding. And so ultimately we will reach a point where the sum of all the partial sums is just a sum of these two numbers. Once we have two numbers, we can use a regular carry look-ahead adder, which again takes in order of log n time, to add these two numbers. So these two numbers will be much larger, and they will have roughly 2n bits, but that's okay. The complexity relation still holds, and then we'll get the final product. So let's now compute the total time of this tree of CSA adders, which is also called a Wallace tree multiplier. So what we have is, since we have this tree over here, the tree has log of n to the base 3 by 2 levels, and each level takes order 1 time because one CSA adder runs in order 1 time. So the total time that is required is order of log of n to the base 3 by 2, which is the same as order of log of n, and the reason being that the base of log does not matter because log to any base and log to any other base, they're related via a constant factor, so those constants can be ignored. So once we have order of log n levels and the time per level is order 1, the total time required to compute these two numbers, let's call them x and y. So here what we have is x plus y is the sum of all the partial sums. And the sum of all the partial sums is essentially the product, the result of the multiplication, which essentially we are producing two numbers whose sum is the final product P. So first thing that we do is we add these n partial sums to come up with two numbers x and y, such that x plus y is equal to P1 till Pn via a tree of carry save adders, and each carry save adder takes order 1 time. And since we have log n such levels, the total time is log n. And finally, we need to add x and y with a carry look ahead adder, which again takes log n time. So as we can see, the final result we can get in order of log n time. So this is the fastest possible multiplier, and this is very, very commonly and frequently used in commercial circuits. So as you can see, this is very fast, and the reason it is fast is basically because of this carry save adder, right? Had we not had the carry save adder, it would have been difficult, but because we have this carry save adder, which is a very fast unit, which can take in three inputs and produce two outputs, where the sum of the two outputs is the same as the sum of three inputs, we can quickly reduce a sum of n numbers to a sum of only two numbers within log n time. And then we add the two numbers, we get the final product, which is the result of the multiplication. So we have achieved our goal of having a log n time multiplier. So this slide only summarizes what we have discussed. Just a quick recap. We use an array of CSA adders to add three numbers to produce two numbers. So we reduce the set of numbers by 2/3 every level, or we divide it by 3/2. After of log n to the base 3/2 levels, we are left with only two numbers. We use a carry look ahead adder to add them. This takes log n time. So the total time as a result is log n. So again, the time complexity is log n. So I'm skipping this slide because we have already discussed the content. All right, so what have we done? What we have done is that we have focused on addition and multiplication in this, in the last three lectures. So now we'll move to other things. We'll move to division, floating point addition, floating point multiplication, and floating point division. So, because this was a long chapter, I divided the slides into two sub slides, right? Two set of sub slides. So one is chapter 7, part 1, and so you'll find one slide as chapter 7, part 1, and the other is chapter 7, part 2. So what we'll do is we'll move to the next slide set, which is part 2. So we'll discuss these four topics in part 2. And so the current part, which is part 1, is over.